Hello everyone, my name is James Ryan, and you are watching Cerebrosplosion. Today, I'm going to derive for you the Schrodinger equation. I spelled that completely wrong. It's the Schrodinger equation. Now, it is commonly believed that the Schrodinger equation came out of left field, that it was created by Schrodinger and it happened to describe particles and their wave functions. Obviously this can't really be true. Obviously Schrodinger would have had some inspiration from different places that he put together to form his equation, but even Richard Feynman said the Schrodinger equation is not derivable from anything you know. It came straight out of the mind of Schrodinger. Paraphrasing, of course. But the point is that Feynman wasn't really that right, because the Schrodinger equation actually is derivable from things we know in physics. In fact, it is derivable from four main things, and the only thing Schrodinger really had to do in order to come up with his particular equation is figure out, one, how to put them together, and two, to make an observation about the fourth thing on this list, which is about plane waves. And Schrodinger's key insight was that you can express a plane wave solution, or you can express a wave with a complex phase, or you can express a wave as a complex number with a particular phase and amplitude. So let's go through these facts. So the first thing is just the Planck-Einstein relation, which states that the energy of light and other particles is equal to E times hf, where E is the energy, h is Planck's constant, and f is the frequency. As I said, this is initially was hypothesized for light, but then thanks to de Broglie, it was found that other particles also can behave as waves, and that this equation also applies for them. Following more de Broglie, this forms one half of the de Broglie relations. The other de Broglie relation, the other de Broglie relation is relating to wavelength and momentum. It basically states that momentum is equal to Planck's constant divided by the wavelength. Right. Third is the very simple equation that E, the total energy, or in this case what we can call the Hamiltonian H, is equal to the momentum squared divided by 2m for the kinetic energy plus any potential energy terms. Just briefly, the way we can derive this is as follows. If we take our kinetic energy, Ke, to be equal to mv squared on 2, and we know that our momentum, P, is equal to mv, then it is clear that mv squared on 2 can be written as mv squared divided by 2m, because then because this is m squared v squared on 2m, which is just mv squared on 2, which is equal to p squared on 2m. Now, the last part refers to plane waves. So first I want to go on a little tangent. What are plane waves? Well, for that we need to go back into wave history. But basically, one of the motivations for Schrodinger to produce the Schrodinger wave equation was a statement by a physicist, basically an offhand comment saying that if matter matter waves existed, then they should satisfy some type of wave equation. It had already been known that other types of waves, such as light waves and water waves, satisfied their own wave equations, which were types of differential equations, which showed how the wave evolved in space and time. Showed how they evolved in time, because we already know how it is in space. But what you find when you do these wave equations is that there are a very simple set of solutions. Apart from the complex solutions, there are these very simple solutions called plane waves. And what a plane wave is basically a wave that is the same basically at all points in space and time, and with only a few very simple properties. It has a wavelength, it has a frequency, and it has a direction and velocity of propagation, Vp. So if you were to take a look at a small 2D section of a particular plane wave, you might find that it's going in this direction, and then if you find that it's going in that direction, it'll have a wave. The wave fronts will look like this, and that'll be the peaks and troughs of the wave. So if you zoom in, you'll find it'll look something like that. And you'll find two things. You'll find that the distance between one peak and the next peak is a particular wavelength, lambda. You'll find that it travels in a particular direction, the velocity of propagation in time, taking with a speed where the peaks travel at the speed Vp, and you'll find that the time it takes for a particular point to wobble from being a peak to a trough and back is going to be a period t, the inverse of which is the frequency, and the frequency is how often it will do that. Now, let's get some quick relations out of the way. We already know from... So, let's get some quick relations out of the way. When we are using wave equations, we like to use things like sine functions and cosine functions. And in this case, we're going to use an exponential function. But when you're using a sine function, if you want a sine function with a frequency of 1 second, say, so that the sine function does this every second or something, you can't just put in sine of t and say, well, t is seconds, because then it won't oscillate it won't complete one cycle every second. It'll complete one cycle every 2 pi seconds. If you want it to oscillate once a second, you actually have to put in sine of 2 pi t. And if you want to oscillate it at a particular frequency, you have to put it in sine of 2 pi ft. The 2 pi factor is important because in order to complete one cycle around a circle, the sine function has to go 2 pi radians, not 1 radian. So this leads to a quantity known as the angular frequency. And quite simply, the angular frequency, omega, is just 2 pi times the regular frequency f. Similarly, when we want to describe oscillations in space, we don't tend to use the wavelength, because the wavelength is kind of like a period. It's a definite amount of space per cycle. Whereas when we're dealing with sines and cosine functions, what we want to plug in is the frequency. So if 1 over the period is the frequency, then 1 over the wavelength is what we call the wave number. So the wave number, which is v with a little dash on top, is equal to 1 over the wavelength, so 1 over lambda. But again, we want to use an angular wave number, so if we times 2 pi and divide by the wavelength, we get k, the wave number. Putting all this together, we can describe waves as sine of this and that, we know that a usual travelling wave function goes such as the following. Sine of kx, so you can imagine this goes up and down with a wave number k in x, minus omega t, which basically says also the wave function goes backwards at each particular point with an angular frequency omega in time, and together these produce a wave that goes to the right if omega is positive, and to the left if omega is negative. Basically, omega t is a translation that moves this wave forward with a particular velocity. This could be a sine function or a cosine function. What Schrodinger realized is that if you wanted to form a good wave equation, it would be better if you had a two-component wave function, or a complex one, which you could easily rotate. So what he did was, instead of sine or a cosine, he did the sine times the imaginary number plus the cosine of the same kx minus omega t, and together this is a complex number that rotates around in space and time, sort of like this, sort of like that. And thanks to Euler, we have a shorthand for this, e to the I, and then you put in the angle, and in this case the angle is kx minus omega t. So therein lies the final piece of the puzzle that Schrodinger realized, and that is that you can express a plane wave as e to the I kx minus omega t. And so now we know that we are looking for an equation with plane wave solutions that look like this. Now, following what I was talking about before about the relationship between frequency and omega, the angular frequency, and also between wavelength and k, the angular wave number, we can see that there is a relationship between the quantities in the wave and the energy and momentum of the particle that the wave represents, or that the wave is part of. We can call them wave packets if you want. And not only that, that we then have an equation representing energy, representing the energy E or H in terms of momentum, which means that if we can figure out how to relate the wave to the energy and the momentum, and then plug those energy and momentum relations into this equation, the Hamiltonian, which basically is a complete description of the system. It basically says total energy is equal to kinetic plus potential energy. Then we will have an energy preserving form of the wave. And furthermore, if we do this in the right way, by using differential operators, then we will form a differential wave equation. Because the other wave equations, the one for light, and the one for water waves and stuff, and the one for just, waves on a string, acoustic waves, those are all differential equations, because they show how waves move in time according to the tiny little differences in the wave, in the amplitude of the wave. Right? The reason when you pull the string it goes back down is because there's difference between the top of the string where you're pulling and where the rest of the string is. So the string accelerates back to where the rest of the string is. And so and then it changes in time based on that. And so those are two parts of a differential equation. You're looking at changes in space and changes in time, and you're relating them. So the question is, what types of differential operators can we come up with to extract the energy and the momentum out of this wave function? Well, the first thing we can try is, what if we try differentiating the wave function with respect to space? So we'll just say, what is the partial derivative with respect to x of the wave function e to the I kx minus omega t, which will be calling from now on a function y, a function psi x of t, which is this little Greek letter psi. And we find that if we do that, thanks to the special way that complex that e to the x factors, e to the x gets derived. What am I saying? Thanks to the special way that that complex exponentials and exponential functions in general are derived, all we get is a factor out in front, followed by the original thing. So since we're deriving with respect to space, the omega t part doesn't contribute, and we just see that if we derive with respect to x, in here we get ik, so ik comes out the front, and then the rest of the function is copied back over e to the I kx minus omega t. So far, so good. So what we've found here is that if we derive the wave function, I'm calling it a wave function now, with respect to space, then we get ik out the front. Okay. What if we derive it with respect to time? If we derive it, which by the way we can say for short that the derivative of the wave function psi is equal to ik times psi, which is a much shorter way of saying it. Likewise, if we take the derivative with respect to time of psi, we'll find that instead of ik, negative I omega comes out, and we'll get that the derivative with respect to time is negative I omega t. Now we're almost done here, but the thing is we've got omega and k, but we're looking for hf and h on lambda. Or are we? So what we can do is we want to reformulate the energy and momentum equations in terms of the angular frequency and the angular wave number. Now we know that E is equal to hf. If we want to write E in terms of the angular frequency, which is 2 pi f, we can say E is equal to h omega on 2 pi. Alright, if we want to do the momentum, we can say that P is equal to h on lambda. H on lambda. We know that since k is equal to lambda on 2 pi, that if we stick that means that lambda, since we know that k is lambda on 2 pi, we know that lambda is 2 pi times, since we know that k is equal to 2 pi on lambda, we can rearrange and say that lambda is equal to 2 pi on k, and so this then becomes hk on 2 pi. Luckily for us, we have a special way of simplifying this. The fact is that h on 2 pi comes up so often after the development of the Schrodinger equation and a bunch of other stuff, and in the Schrodinger equation, that physicists decided to just get rid of the 2 pi factor and say, look, let's have a reduced Planck's constant, h with a bar, h bar, that is equal to h on 2 pi, and let's let this h bar absorb the 2 pi, the 1 on 2 pi into it. So now, instead of h omega on 2 pi, we can just say h bar omega. And instead of hk on 2 pi, we can just say h bar k. So now we've transformed our relations. Instead of hf, the Planck's constant times the frequency, we have Planck's reduced constant times the angular frequency. So it's been divided by 2 pi and times by 2 pi. So it's the same. And instead of having h on the wavelength lambda, we have h bar times k. And actually this one is a much simpler formula because it's directly in terms of the wave number. So it's much easier to keep track of and use. So now that we know that energy is just h bar omega and momentum is h bar k, we can better use the differentials we came up with. We can actually see that if we were to take this function here, times it by I h bar, then you would get, well, let's just rewrite them on a new paper and see what we get. If we were to, we know now that if we take the derivative of with x with respect to psi, we get ik psi, and if we take the derivative with respect to time, the partial derivative of psi, then we get negative I omega psi. If we times both sides of this equation, here with negative I h bar, so we got negative I h bar times d dx psi, then we get that is equal to this thing times negative I. I times negative I is just 1, and so then you just get h bar k psi, or momentum psi. So we've found an operator, negative I h bar times the derivative, that when applied to psi gives psi back times the momentum. That means that the momentum, that psi, that we can describe this in terms of eigenvalues and eigen functions and eigenvectors and stuff. Basically, here psi is an eigenfunction and p is an eigenvalue of this operator, the momentum operator. The momentum operator, when applied to at least this particular plane wave, will give back the plane wave times a factor p, which is the momentum. So all we have to do is derive on a tiny little bit of this wave, then figure out the derivative, times it by this factor, these extra factors, negative I h bar on top, divide by the wave, and we'll get p, the momentum. So we've found a way to extract p from the wave, and we've done it using differential operators, which means we're well on our way to forming a wave equation. Performing the same thing with the time derivative, I shouldn't do that. Compartmentalizing things too much, but it's a bad habit of mine. Anyway, if we do the same thing with this one, we can see that if we times both sides by I h bar, then we'll get what the expression we're looking for. So now we have I h bar, no negative factor here, times d, the partial derivative with respect to time of psi is equal to negative I times I, so that's 1. So just h bar omega psi, which is equal to energy psi. Perfect. Which we can also write as h, the Hamiltonian psi. Hamiltonian and the total energy mean the same thing, but what we will later find is that we'll tend to use the Hamiltonian, we'll tend to use the energy to refer specifically to this operator, I h bar, partial derivative with respect to time, whereas whereas for the h, we will use it to refer to a different operator, the one we're going to find, that also gives the energy, but in terms of the momentum, which is what we're about to do. Since we know that IH delta t psi is the energy times the wave function, and negative I h bar delta x psi is the momentum times the wave function, we can now plug these two different things we know into the original function. E is equal to p squared onto m plus potential energy V. Okay? Now, basically what we're going to do is we want to treat these things as operators that act on the wave function. So what we do now is we're going to actually get rid of the psi's. We were using them to form it, but now we're going to cancel all the psi's out, and we're going to find out the following. We can take this direct shortcut and say I h bar delta t is equal to the energy, as long as then you apply it to the wave function later, as long as we put a psi on both sides. And the same for this one. If we get rid of this psi here and psi here, then all we have is that this thing here is equal to the momentum, as long as, of course, we apply it to a particular wave function. So, taking these to be exactly these operators, what we find is that on the left, we will have I h bar delta t is equal to p squared on 2m. So now we're going to square this operator, and you can say, well, how do you square a differential operator? Well, if you want to square a derivative, basically it just means to take the derivative twice. So the negative I squared becomes just a negative, and the d dx squared becomes delta squared delta x squared. And finally, the v we just put on the end plus v. Then, after plugging in, then we can apply this whole thing by timesing it to psi, and we'll get, putting the psi there, and the psi there, we get a one-dimensional Schrodinger equation. And that's how you do it. Now, very quickly, what we can do, if I just get another piece of paper, is we can expand this to other dimensions. The wave function in more than one dimension is just, instead of having kx, k can be a vector which points in a different direction. And gives you k, which points in different directions and gives you different values in different directions. But basically, if you decompose it, you just get a k in the x direction times x, plus a k in the y dimension plus times y, plus a k in the z dimension times z, and a minus omega t. And if you do the derivative on this, you'll find that you'll get three different momentum operators, one for each direction, x, y, and z. Then, of course, when you square the momentum, of course the momentum operators go so that the total momentum p is equal to the square root of k of px squared plus pz squared plus py squared. I'm doing this in the wrong direction. But then, of course, p squared is just equal to px squared plus py squared plus pz squared. Since the derivative operators are the same, then we get that p squared, instead of being equal to negative delta squared delta x squared, we find that it's equal to negative delta squared delta x squared minus delta squared delta y squared minus delta squared delta z squared. But physicists and mathematicians have a shorthand for when you take the derivative in the double derivative, or in all three directions at once, and then add them together, or in this case they're all being minused, and that is the Laplacian. And the Laplacian is just described by this symbol, an upside down triangle called del with squared. So it's just del squared. The square, of course, represents that all of these are squared. They're together, they're being derived twice. And of course, for the momentum, this has a negative in front of it. So this is p squared. And so there was one other problem I had in here, in this equation, that I sorely missed out on. I made a mistake. Obviously, this whole thing here, this part here, is being divided by 2m. This top half is the p squared, this bottom half is 2m. But now that we have now that we just have a triangle, the Schrodinger equation becomes much simpler. It's just negative, what did we have before? Oh crap, I've lost track of all the pain. It's just, not negative, it's just I, h bar, delta t of the psi. Now, much simpler, it's just negative, and again, we forgot another thing, it's not just, what is it that I forgot? I forgot the h bar, so there's a h bar here as well that I've forgotten to put in front of the p. So it's h, and that is also squared too. So if you just ignore that part, what I meant to write before was I meant to write delta squared on delta x squared times h bar squared on 2m, but I didn't get around to it. But now we can see that it's minus h bar squared on 2m times this Laplacian applied to the wave function plus v applied to the wave function. And this is the Schrodinger equation. It describes how the wave function evolves over time, based on how it is in space. If you wanted to solve this analytically, there are different ways of going about it. I'm going to show you in a video soon how to separate the time and space variables so you can get the time-independent Schrodinger equation. But for the moment, just know that what you can do is if you divide both sides by I/h bar, you get a new equation that shows you how this, how delta, that shows you, that gives you the equation in terms of change in time of psi. And then using a computer you can numerically integrate, which basically just means you change psi, you calculate change in psi, and then you change psi by it by adding it on in tiny little amounts, and you keep doing that, and that will give you a very simple way to compute the Schrodinger equation. And I will eventually work our way towards doing that. So yeah. But just to reiterate something that I mucked up on, the correct equation before for the one-dimensional Schrodinger equation case, just write it all down on one paper and to you know, make it all good and the same. In one dimension, the Schrodinger equation is I h bar delta t psi equals negative h bar squared on 2m. This is the part I forgot. H bar squared obviously comes from the momentum. We had negative I h bar. Then we're squaring all that, then divided by 2m. The I times I becomes the negative. Even though it's negative I times negative I, it doesn't matter. Still the same. Times the second derivative with respect to space of psi plus the potential energy times psi. And then when we go to the three-dimensional case, the only thing that changes is this operator here. For the momentum is replaced with what we call the Laplacian, so we get I h bar delta t of psi is equal to negative h bar squared on 2m Laplacian squared or del squared psi plus v psi. Okay, and one important thing to note that is that psi is specifically isn't just a variable, it's a function. It's called a wave function because it's a wave and a function, and it's a function of in the one-dimensional case of x and t, and in the three-dimensional case, so that's one-dimensional, three-dimensional, it's a function of x, y, z, and t. So the three spatial dimensions and time. But we usually represent that. We can also represent that as one big space. So like x bold or something. Make x like super bold. And time, or maybe like a big X or something. And the last but not least is to not confuse the wave function, which is a definite function with that can be written analytically or stored as a bunch of values in a computer for space and time, and to not confuse it with the abstract state of a particle psi kept, which is written like this. This is different. This is an abstract representation of the state in a Hilbert space. This can be equivalent to the wave function, but really this is a more abstract object. It contains not only all the position information, but also the momentum and any other thing you want to know. Specifically, you could also store these values in a computer, but that would be in a specific basis. And if you store it in like a space basis or a time basis or something, then what you get basically is a wave function. In fact, to be very rigorous about this, what we say that the wave function psi of x, right, is equal to is defined as, so we use 3 equals arrows and the word def. This is technical, but basically the projection of the state psi onto x, which basically means the wave function gives you the probability amplitudes for finding the state's psi, the whole particle state, at a state x. That's technicality, and if you haven't gone over the quantum states yet, or bracket notation, You won't understand what that means, but the point is that these things, even though you might see them written occasionally the same, you might even actually see the Schrodinger equation written in terms of these vectors, which you can do. There is a technical and mathematical difference between them, and so it's important, I think, early on to realize that these are slightly different objects. Until then, if you're just using wave functions, it's better to specifically either say this is a wave function of x and t, psi of x and t, or just use psi, and that way, as long as you don't enclose it in these special brackets, there's no confusion. You are dealing with a regular function, not with what this is called a state vector. Alright, so thank you for watching. My name is James Ryan, and I have been your host. You've been watching Cerebrosplosion, and I think the next video we can maybe look forward to is how about we can split the Schrodinger equation into its time and space parts. I'm also looking forward to making more basic quantum mechanics videos and quantum physics videos that show the development of the theory from more basic steps. How do we get the Einstein-Planck relations? How do we get the Broglie relations? How did they come up with those? What experiments happened? And so on. But I'm very happy to have made this. I know it's a bit clumsy video. You know, there was a lot of scuffling around for paper and stuff, but I'm really happy I finally made this, because I've been thinking about making a video like this for a long time, and I finally got around to doing it. Got past my fear and did it. So thank you for watching. My name is James Ryan, and I've been your host. And always keep learning.